My name is Zeping Yu, and I'm supervised by Professor Sofia Ananiado. My research topic is understanding and improving LLMs through mechanistic interpretability. And here is my research. First, I focus on understanding how LLMs perform basic capabilities internally. Then I focus on improving LLMs capabilities during post-training. And here is the outline. I will introduce what is mechanistic interpretability and why mechanistic interpretability is important. Then I will introduce the main techniques in this field. What is mechanistic interpretability? MI is a new research field started in 2020. The goal is to reverse engineering the internal mechanism of transformers in order to understand the reason behind LLM's decision. For example, when we ask LLMs which is larger, 0.9 or 0.11, most LLMs will answer 0.11. But we don't know why this happens because it predicts falsely. And as a result, we can't trust LLMs very much because we don't know whether they will have other ridiculous faults like this. So mechanistic interpretability techniques can help people understand why LLMs produce falsely. And in this case, the reason is that 0.9 and 0.11 activates the neurons and parameters related to the versions. So in this situation, 0.11 means the number 11 version, and 0.9 means the ninth version. So the model thinks 0.11 is larger than 0.9. So in order to solve this problem, we can design some methods based on the analysis, such as adding prompts before the sentence. If we say 0.9 and 0.11 are numbers, then the LLMs can answer directly. The main goal of mechanistic interpretability is to create safer LLMs. Most abilities of LLMs are emergent ability. With the emergent stage, LLMs have many harmful behaviors and we don't know the reasons. Therefore, if we can understand how LLMs perform internally, we can try to control LLMs' behaviors and create safer LLMs. At the same time, mechanistic interpretability can help create better LLMs. We can boost the trustworthiness and improve LLMs' abilities using interpretability-driven methods such as model editing and model merging. Next, I will introduce the main techniques in mechanistic interpretability. I will first introduce the background of decoding LLMs. Then I will introduce the importance attribution methods, including causal-based methods and logic-based methods. At last, I will introduce how to use mechanistic interpretability to improve LLM's capabilities. One of the main background is the residual stream in decoder-only LLMs. In decoder-only LLMs, each layer's output is the direct sum of this layer's input, the attention layer output, and the FFN layer's output. Therefore, the final layer's output can be regarded as a direct sum of many attention layer outputs and many FFN layer outputs. Since the final embedding contains important information related to the next token prediction, this information can be separated into one or several attention or FFN layers. And another background is the definition of neurons in FFN layers. Equation 5 shows the matrix level computation of FFN layers, which has two MLPs. The matrix level computation can be regarded as the vector level computation, as shown in equation 6 and 7. Specifically, when we say the number case neuron, we mean the number case column of the second MLP, which is the vector. And this vector's weight is computed by the inner product between the FFN input and the number case row of the first MLP. As a result, the FFN layer output can be regarded as the weighted sum of many FFN neurons, where each neuron is a vector. Another background is the definition of neurons in attention layers. This is one of our publications in EMLP 2024. In this work, I found that the attention head output can also be regarded as weighted sum of attention neurons, where the number case attention neuron is the number case column of the output matrix in this head. And this is because the attention head also can be regarded as the matrix level computation of two MLPs, similar to FFN layers. As a result, the final embedding can be regarded as a direct sum of attention and FFN neurons. And if we can identify one or several most important neurons for some tasks, we can use model editing techniques to edit neurons in order to change the LLM's outputs. For example, we can locate the important neurons storing the false knowledge and correct them by editing them. And then I will introduce the attribution methods. The core problem is how to identify the important neurons. One of the well-known methods is causal-based method. The core idea is to perturb the hidden states and see how much the outputs are affected. If the output is affected much, it means this hidden state is important. For example, in this figure, they found that the entity position's medium layer hidden states and the last position's higher layer hidden states are important. Another attribution method is named logit-based method, based on the residual stream. As we introduced in the background, the final embedding contains important information related to the next token. Therefore, we can compute each neuron with the unembedded matrix and calculate the top tokens. If the next token ranks very top, it means this neuron is important. And we can also calculate the inner product to identify the most important neurons in shallow layers. Until now, I have introduced how to identify the important neurons in LLMs. And after this, we can understand how different tasks perform internally. For example, we can analyze the information flow of factual knowledge. In this study, they find that the important places are the shallow FFN layers and the medium attention heads. And this is an analysis of arithmetic operations. The shallow FFN layers process the numbers and operators, and then the attention head transfer the information into the last position. And finally, the deep FFN layers help generate the results. And this is one of our publications in EMLP 2024. In this work, we explored how LLMs perform arithmetic operations at the neuron level. Overall, it has 4 stages. First, there is a feature enhancing stage in shallow FFN neurons. The shallow FFN neurons are input-related features. Then there is a feature transferring stage in attention head. After this stage, all the features are transferred into the last position. The most important role is the arithmetic head. This head's role is to activate the FFN neurons related to the answer. If this head is replaced by 0 parameters, the accuracy drops much more sharply than other heads. Finally, there is a prediction enhancing stage among deep FFN neurons. Another work is understanding and enhancing latent multimodal reasoning in LLMs. This work is published in EMLP 2025. The latent multimodal reasoning is important for LLMs. For example, when we ask Mozart's mother's boss is, we hope that LLMs can directly answer Leopold, which is the correct answer. We find that even though the first hop and the second hop are both correct, the latent 2-hop accuracy is only 52%. This means that the mechanism has some problem because the knowledge of both 2 hops is stored in the LLMs. To explore this reason, we first explore the single-hop mechanism of knowledge prediction. We find that there are two main states. On the entity position, it captures Mozart's features into the medium layers. Then on the relations position, it predicts the correct entity in the deep layers. Then we explore why the two-hop accuracy is low. We use two analysis method and find that the main difference happens at the relation position. The false answer captures the high-layer information falsely. Here, the logic flow method focuses on the neurons, and the causal tracing method focuses on the layers. Both methods have the same conclusion. Then we can understand why this happens. Decoder LLMs are causal models, so the hidden states of Mozart's mother are the same with Mozart's mother's both is. So in two-hop cases, even though the higher layer contains the bridge entity's information, this information cannot activate the early layer states. As a result, the model predicts the false answer. In order to address this problem, we designed the back attention module. This module uses the lower layer as the query and the higher layer as the key and value. Using this module, the model can learn how to capture the higher layers information back into lower layers. As a result, the important parameters storing the second hop or later hops information can be activated. And here are the experiments when adding back attention in pre-training. When adding back attention on a one-layer transformer, the accuracy is improved from about 83% to 93%. And when adding back attention in post-training stage, the accuracy can also be improved much. We conduct experiments on 5 reasoning datasets and five LLMs, including Llama, Mistral, and Queen. On all the datasets and LLMs, the back attention module can help improve the latent multi-hop reasoning ability very much. And at last, I will introduce other methods to improve LLM's capabilities via interpretability-driven methods. One method is to design interpretability tools to let users know which image patches are important to predict the false answer in order to mitigate the visual hallucination. For example, in this image, when asking what is the color of the left bottle, the LLM answers red. However, this is a false answer because the correct answer is purple. However, we don't know why it answers falsely because many reasons can cause this false. For example, it may misunderstand the left into red, or it may misunderstand the purple into red. Using the interpretability tool, we can understand the reason is that the model pays attention to the bottom of the left bottle here. Another method is to locate the false knowledge and edit these parameters to correct the knowledge. For example, in this work, they locate the false knowledge in alpha neurons and edit them. Also, we can identify the parameters containing toxicity and then edit these parameters to reduce toxicity. In this work, they reduce the coefficient score of the toxicity neurons in order to reduce the toxicity. We can also use model editing to reduce the gender bias in LLMs. In this work, we locate the neurons in both shallow and deep layers and use zero parameters to replace these neurons in order to reduce the gender bias in LLMs. Besides model editing, we can also use model merging method to mitigate the catastrophic forgetting problem in LLMs. We know that in LLMs and multimodal LLMs, they use a visual instruction tuning method to modify the parameters in order to learn the visual ability. However, after the fine-tuning stage, the original language ability is reduced much. For example, we can see this figure in the see the right figure. The green part is the language ability of the fine-tuned multimodal LLMs, and the orange part is the original LLM's language ability. So the language ability is reduced very much. And we know that the multimodal LLMs, when we use the multimodal LLMs, we not only require the visual ability, but also require the language ability. So this goal is to keep a balance between the language ability and visual ability. And in this work, we design a neural level parameter fusion method to mitigate the catastrophic forgetting in multimodal LLMs. The hypothesis is that during post-training, the learned capability is concentrated in only a few parameters. So if this hypothesis works, we can locate the important parameters during fine-tuning and only modify these parameters and reduce the change of the other parameters. As a result, the learned capabilities are kept and the original language ability is not reduced much. And in the experimental results as shown in these tables, on 2 LLMs and 13 datasets, the language ability is kept and the visual ability is dropped slightly, but the overall ability is improved. So as a result, the catastrophic forgetting problem is reduced. And here are all the introductions, and thank you for listening.